Now, if you know me for long enough, you'll come to realise that I like to get stuck into a lot of coding projects that I've created over the past few years. Whether it's my Linux distro, LiveGOS, that I've been working on for the last 3 years, which runs on my phone, and I also daily drive it on my new laptop. Or that educational device for kids that I made, the NanoPlay, that was meant to compete with the BBC Microbit. Or what about that social network that I made, which is totally not a rip-off of Reddit? Or even that clone of Minecraft that I built for my calculator called Signcraft. There's not only the first C project I ever made, aside from Hello World, but also my first ever attempt at building a 3D rendering engine. You get the idea. Basically, if you go to my GitHub, you'll notice that my contributions graph is worryingly green. Mostly. Apart from in 2021. So it's no wonder that when I told my mates on Discord about the new programming language that I was building, they replied to me saying it is so James Livesey to be doing this. I mean, it's not even the first programming language that I've made either. My first programming language was Atto, which is pretty basic. I mean, it was a clone of the basic programming language of the 80s, and similarly, Atto's mission was to introduce beginners to the concepts of programming. And I'm proud to say that not only did it get a lot of attention on Hacker News, but a final year university student actually used Atto as part of their teaching course. And a bunch of school children got introduced to the world of text-based programming languages through Atto. I mean, how cool is that? The reason why I'm building a new programming language, though, is because Atto was far from perfect, being the first programming language that I've ever developed. While you could do some cool stuff in it, it never supported object-oriented programming, and some of the syntax was very much like BASIC, with all the line numbers and stuff you have to add in. So you can never really do any big, serious projects in it. Atto code also only ran in the browser because the interpreter used a lot of JavaScript, so you couldn't run it on microcontrollers either. Though I did consider rewriting the interpreter in C at one point, but it never really gained fruition. So this new programming language, Voxel, I've built from the ground up to be efficient, portable, easy to use, basically everything that's great about modern programming languages of today. The runtime is all written in C, which allows it to run almost everywhere, and there's a gigantic C header file that you can just copy and paste into your own project, and boom, you've got a voxel runtime that you can embed and do stuff with. A bit like the Lua programming language. Not only that, but you can run your voxel code on not just your computer, but also on a little microcontroller like this ESP32S3 that I've got here. Cool, right? Alright, so now that I've told you a bit about what Voxel is and the ideas behind it, let's have a actual look at how Voxel works. So this is just an example of how to embed Voxel in some C code. Here we're basically just importing a config file for Voxel, which looks like this. It allows you to define all your types and other useful options in Voxel, as well as features which are part of studlib or studio, because you can switch out your standard library, your C standard library, for something else, which makes it ideal for embedded systems. This is actually code for the Voxel runtime, so we are creating a new Voxel context, which basically defines the world in which our script is executing, and the global scope and everything. And then here we're just reading in a bytecode file, and we load it into memory here and tell the context the length of the code. We initialize it, and then while any executors are running, so an executor is basically like a thread in Voxel, while any executors are running, we step through the context. So it works like that. So it's pretty basic, simple to implement a runtime. And there are also ways in which you can define your own custom system calls and stuff, which I won't delve into too much right now, but it's just a simple case of importing this gigantic header file, which is just amalgamation of these header files on the left here, which are all combined into one big file, and that contains the runtime code as well as any supporting features which you can turn on or off as you desire, depending on how much space you have on your target system. So here I have a new Visual Studio Code window, and I'm going to write a bit of actual Voxel code itself. So let's just start with hello world. So import IO and then io.print line hello world. So we can run that by going, so first we have to actually compile it, of course. So vxbuild is our compiler, and that's written in JavaScript running in Deno, but I soon hope to write that, rewrite it all in Voxel so that it's all self-hosting. So we can go hello.vxl, output it as hello.vxc, and vxc is our bytecode format, which has been created for Voxel. That compiles it, so it's basically performing a bunch of static code analysis, it's parsing it, and it does a bunch of things with the symbols so that we can decrease the amount of code by shrinking the symbols. So if we go to hello.vxc and look at the bytecode, here's an example of how long a symbol is in the bytecode. We can actually turn off the behavior by going no mangle, and that will show us the full names that are assigned to each identifier or like variable name. But that's a really long way of storing it, and of course our bytecode grows a lot, so we optimize that by renaming them to numbers, numerical values instead of strings. So that's a really good optimization. And we also remove any dead code or code which basically is never going to be executed. So any unused functions in libraries such as the IO library, so our stream functionality in IO are removed because we don't use it, as well as any if statements and things which will never be executed because their condition always evaluates to false, for example. And to get a good idea of what it looks like without dead code and elimination, this is an example of how long it will look like, because it imports all of the IO library as we did, and it will also include a lot of core features which just end up going unused. So it's really a difference of 6 kilobytes here versus, go to the top, 207 bytes. So definitely an optimization. The next demo I'll show you is a for loop. So I is nor I is less than 100, I plus plus, a classic. This is iteration I. Do that, and then if we go, I haven't actually executed the hello world code, have I? So to do that, we can go voxel hello.vxc, and that says hello world, of course. So I'll just compile this one up here, like that, and then if I do voxel hello.vxc, voxel is our runtime. That's what that command is. That's outputting every iteration, and we can quickly go bigger if we really wanted to. And as you can see, it goes nice and fast. I think it starts to slow down, so it's a bit more noticeable if we multiply that by 10. Yeah, but yeah, you can see it generally is pretty fast as a programming language. The next demo I'll implement is use of functions to do a Fibonacci sequence. I do have a reference written in Python over here, so I'll just write this in Voxel. So if n is 0, then return 0. If n is 0, sorry, if n is 1 or n is 2, return 1. Otherwise, return. And this is a demo of recursive functions. N minus 2. And then I got print line Fibonacci at. I really can't spell today. There seems to be a common theme on this channel. I swear I can actually spell when I'm not being filmed. At index 9. We should probably actually compile it first before running it again. says 34, which is the correct answer, which is a relief. We might actually benefit from chaining these commands so it all happens all at once. That's a bit better. We could also generate Fibonacci numbers and put them into an array, or a list as it's called in Voxel. So for I it's 0, I is less than 20. 20 is a good number for it to not take too long. And then we just want to go sequence.push Fibonacci I. And you can print that sequence. I know it's not the most efficient way of doing it, because you could just generate each next Fibonacci number in the for loop, but this is just a demo of how to use lists anyway, so there you go. And that looks like it. Well, we shouldn't really start from 0, should we? We'll start from 1, and yeah, that looks like it's correct. Each previous 2 numbers add to form the next number, so yeah, it's a good demo of that. And we can also show you how to do error handling. So obviously you can't really use n being less than 0, so we could go throw, we can throw anything, but a preferred way of error handling in Voxel is not to do object-oriented programming, like throwing an exception class, but it's actually to use an enum. And that's because it's more space efficient compared to if we import all the OOP functionality within our program. So we'll just do enum and then Fibonacci error, we'll call it, and then is less than 0. And if we attempt to do that, -2, let's say, it'll show you that there is an unhandled exception down here. Encountered error code. Hello, Fibonacci error is less than 0. So that's quite useful. We could always go try. If I remember correctly, it's a long time ago since I implemented try catch. See if it even still works. I can't remember if we can actually. I don't think we can actually. Get the actual value that's been thrown itself yet, but that'll be something that will come soon. We can go io.print line. Oopsie. Yeah, we actually do need to put. Oopsie. I don't think we can print out E yet though. Oh, we can. That's nice. So I did implement that then. Equals Fibonacci.error dot is less than 0. Oopsie, and yeah, it's true. We can actually obtain the original identifier for the Fibonacci for that enum entry by going get enum name, I think. It is something. Or it could be entry, I think. It's one of them. I would look into the code, but trust me, you can actually get the name out. It's literally what we do when we throw something. Let's just rethrow that again. Yeah, you can see that here we actually tell you the enum identifier and where it is. So it's in hello.vxl, and that's code 1. You can go code 400, for example. And you'll see in our bytecode we actually define that here, so that it can be reverse looked up later on. And we can actually turn off that behavior by going no enum lookup. And you'll see that gets removed, which, saves on space, but is a bit less helpful. Yeah, you'll see, for example, in the previous one, it just says unhandle exception 1, whereas now that we've re-enabled it, it gives you a more descriptive error message like that. So that is a few examples of basic Voxel features. Here's an example I prepared earlier of object-oriented programming. So here I defined a class to model a car using physics. I'm not sure if it's 100% accurate. I'm not really a physicist that much. I'm not well qualified for these kind of things, but this is just a little example. And you can see here that we define a few properties and we have a few methods to step through time and print out or return a string which gets all the information for the car. Whether or not we can open the doors. So this is a getter function. So here we just go. We basically act like a property, and then we have accelerate and brake, which increase and decrease our acceleration property on the fly. And in this example, we start stationary. Let's actually run this. So car.vxl, car.vxe, and car.vxe. Here we start off stationary, then we start accelerating, and then we decelerate again. Here's a little example. We could extend the class actually, so we could have class truck extends car, and we could have a function to like open the trunk or what's the name for the back bit of a truck? Open back doors, we'll call them. So let's go back doors. We could make it a setter, or let's do that. So private fields start with an underscore, just easier to implement it like that. Back door is open. And then get door is open. So we can return private field. Set backdoor is open. If so can open doors, we can always create an error. So edum cannot open doors, or vehicle error. We should rename this to vehicle. Cannot open doors if we can close the door, of course, while this is still on the go, but we can only open it when it's stationary. So throw vehicle error dot cannot open doors. Otherwise we'll go just dot backdoor is open equals is open, and then we could go info return super.getInfo plus door is we can't redo ternary functions yet, that's not been implemented yet. Open let's just put in the boolean, so this dot backdoor is open. Ignore that it says James' car. In fact, let's rename that. James's truck. Hopefully this can compile. This is an example of an error. I'm not sure what's gone wrong there, but expected identifier. I've got keyword instead. Can we do that? There's something for me to investigate with Voxel there, but let's remove that for now. Oh, it doesn't like. Ah, I know where it's looking. Yeah, I should read the line number, shouldn't I? We can't have this at the start of the property name. Nice, okay, so in this example, it is printing out backdoor is open is false, along with all that info. And we can go James's truck dots backdoors true. So first one we should see that it's backdoor is open. But if we try and accelerate and then open the back door, we should see that it throws cannot open doors. So yeah, there you go. That's a little brief overview of using all sorts of features in Voxel. That's just the tip of the iceberg. There's so many different other things that you can do that I'm adding day by day. So yeah, be sure to check the GitHub where there's lots of documentation that I've been writing for things such as multi-threading and all the operators and enums, of course. And yeah, feel free to have a play. There's lots of test suites that I've written, test cases rather, which I use to determine if there are regressions in Voxel. So they are really good examples of the things that Voxel can do. And I hope to write some more examples as well. So yeah, have a look. But anyway, let's get back to the other James and get on with the rest of the video. So why am I actually building a new programming language? Well, aside from it being a fun and cool project that gives you something to brag about, there's actually also a more practical reason, and that's because it's part of a bigger project that I'm working on. I'm trying to make a portable pocket computing device that is designed to be very energy efficient and also can last for ages on a single charge. So I guess it would be pretty useful in an apocalypse that will no doubt happen sometime soon due to climate change and all that. I've even built a prototype so far. Ignore the messy wires. Here I've got a sharp memory display, which is monochrome and super energy efficient as well, but also has a very high resolution for an LCD display like this. And unlike e-ink and other low energy display technologies, it can also support really high refresh rates. The end result is that I'm hoping that it will look like a BlackBerry, as it will also feature a QWERTY keyboard below the screen. I also plan to have a plug-and-play module system that lets you install a module onto the back of the device, and that would enable things like Meshtastic for long-range radio communications, 4G LTE, NFC, perhaps even a camera that can take low-resolution photos, and maybe even scan things like barcodes and matrix codes, which could be useful for certain industries. And basically any other custom modules that I can think of between now and when I complete the project. Where does Voxel fit into all of this then? Well, I would like users to have some sort of way of writing their own apps that they can then install onto the device, and Voxel will be the programming language of choice for that. I'll also be planning to rewrite the compiler in Voxel, so with any luck, and hardware permitting, because there's only about 8 megabytes of RAM on an ESP32 that I've got, you'll be able to write Voxel programs on the device itself, compile them, and run them. So that's my idea and my programming language. If you're interested in the development of my programming language, then you'll probably like my previous video where I implemented for loops in Voxel. But do be warned, the video is like an hour and a half long, so make sure you've got absolutely nothing else that you need to do, and also that you don't fall asleep while watching it. But yeah, I hope to upload more videos about Voxel and the mystical device that I'm working on soon. So if you'd like to see them when they come out, be sure to subscribe. But otherwise, thanks for watching, and I hope to see you soon.